Okay, let's move on. In this lecture, we are going to talk about the matrix factorization, specifically LU factorization or LU decomposition. Okay, first of all, what is the factorization of the matrix A? So the factorization of the matrix A is an equation that expresses the matrix A as a product of the two or more matrices. For example, in the previous lecture, we would talked about the matrix multiplication, right? So something like the P times C is equal to A, right? Right. So in this case, this is the this is kind of a synthesis that combine the effect of the two or more linear transformation into a single matrix, right? However, the matrix factorization is a reverse step. It means that from the original matrix A, we can decompose the matrix P times C to analyze this original matrix A. Okay, so this is the factorization of the matrix A. Then what is the LU factorization? Actually, there are several kinds of factorization. So in the remaining course, we will talk about the several factorization technique. But today we are going to talk about the LU factorization. Okay, so actually, LU factorization is motivated by the common industrial or the business problem of solving the sequence of the equation, something like the AX equals B, AX equals B2 through the AX equals B4, PP, like that. In this case, the matrix A are same and only difference here, B1, B2, and PP, right? So what is the straightforward solution? What is the straightforward method to solve this sequence of the question or the sequence of equation? If the matrix A is invertible, right? If the matrix A is invertible, we can solve this equation something like A inverse A times X through the A inverse B1, and it should be I or identity matrix, right? So solution will be the A inverse times B, right? B1, right? So if A is invertible, we can find the A inverse, then compute inverse B1, B2, so on, right? Like this term, like this equation, right? However, in some case, it is more efficient to solve the first equation here. Let's say this is the equation 1, and the first equation by row reduction and obtain the LU factorization of matrix A at the same time, and then remaining equation in 1 here solved with the LU factorization. So in other words, if we can decompose this matrix A into the L times U, then we can more efficiently solve this sequence of the equation by using the L and U. Okay, so that's why we study the L factorization. Okay, so from now on, let's find out what it is. Okay, so first of all, there's one assumption. Matrix A is the m by m matrix that can be low reduced to an echelon form, okay, without low interchange, which will be generalized later. So it means that there is if there is a matrix A, to find out the echelon form of the matrix A, we can use the several kinds of the row operations, such as the interchange, scaling, or the row interchange, right? But row interchange. Okay, let's summarize again. Row replacement, row scaling, row replacement, scaling, and row interchange, right? So first of all, let's assume that there is no interchange in the matrix A. It means that there is the case something like this, right? So in this case, we have to use the row interchange to interchange this row, right? So okay, let's assume that there's no such case here. In here, the LU, but we will generalize this in later, so you don't need to worry about that. Anyway, so LU factorization of the matrix A is written as the matrix A is equal to L times U, where L is the m by m unilower triangular matrix with 1 on the diagonal, something like this. And this term whole zero, and there is a constant values here in the left lower side, right? This is the matrix L, and matrix U is the m by n echelon form of the matrix A. So in matrix U, there is the pivot position here, right? And there is the zero value under the pivot position. Okay, let's draw. Okay, let's draw like this, right? And there is the non-zero values here, right? Or zero values anyway. So, but this point definitely should be the non-zero values, right? So this is the echelon form of the matrix A, right? So we can represent the original matrix A as a matrix L times matrix U. Okay, from now on, let's talk about the what is the matrix L and what is the matrix U, and what kinds of property they have, and how can we solve the matrix equation by using the LU decomposition factorization technique. Okay, so before starting how to construct the L and U, we should look at why they are so useful. Okay, so why they are so useful. Okay, first of all, when A is equal to L times U, then the matrix equation AX equals B can be written as the L times UX is equal to B, right? By just replace this one to this one, right? Then we can introduce the one more hidden vector y. Okay, let's use different color. Y for ux here. Then we can represent first equation as the Ly times b, right? Then if we find the vector y, then we can find the solution x using the ux is equals to y, right? So in other words, instead of solving the ax equals b directly, we can decompose this equation into the two sub problem as the ly is equal to b, us is equal to y. Okay, so in other words, if you see this row figure, rather than solving this. Okay. Um, Rather than solving this uh, vector x from the P and matrix A directly, we can decompose the matrix A as a L and U, and first we can find the matrix vector Y here, then we can find the solution X by matrix U. As you can see here, if you think okay, so someone of you say that, oh, comparing when we compute the ax equals b, there's just one multiplication. But when we solve like this, there's a two matrix multiplication. Then we can say that this one is so much efficient than this one, right? But the answer is no. Why? Because of the property of the matrix A, matrix L, and matrix U. So, I mean, the shape of the matrix L and U make the problem solving procedure easier than the AX equals B. Okay, let's see the why. Okay, so to conclude, each question is easy to solve because L and U are triangular. L matrix looks like this, U matrix looks like this, right? Why? There are detailed numerical note. If you don't need to remember whole of things, but just try to understand why this LU decomposition based problem solving method is much easier than the original AX equals B. Okay, so here is the description. Okay, let's say there is a matrix A with an n by n matrix, and if n is the moderately large, let's say n is larger than the 13 or the 1000 or 1 million, something like that, then compute the LU factorization of A takes this plot. Plot means just floating point operation like the multiplication, division, addition, something like that. Because so this number of the operations determining the computation time of the algorithm. So anyway, so analytic computation take some time like this. Whereas the finding A inverse require the 2 and 3 flops. Okay, then solving LU, LY is equal to B, UX is equal to Y require the 2 n 제곱 flop because this is a triangular system. Multiplication B times A inverse also require the 2 n square flop. Let's please think about something like this. Okay, compare to this one and this one and this one. Okay, so here, then the total operation is like this one plus this one plus this one. Okay, comparing to those number of flops, we can say that by using the LU decomposition, we can have the computational efficient than A inverse times B. Okay. Then if the matrix A is sparse, actually in the many cases, the original matrix A is sparse, not a dense matrix. I mean, the matrix A looks like something like sparsely exist and remaining values are 0, like that. So in this case, the matrix LU is also sparse, so there are so many efficient way to solve the sparse matrix, right? We cannot deal with this technique, but there are so many techniques to efficiently solve the sparse matrix. But the inverse of matrix A is likely to be dense. Even though matrix A is sparse, inverse of matrix will be the densely exist. Something like that. So in this case, the solution Ax could be with the LU decomposition much faster than using the inverse of A. Okay, so this is the why the each equation is easier to solve using the LU decomposition. Okay. Okay, here's the example. Let's say there is a matrix A, something like this, right? And we already decomposed this matrix A as a matrix L and matrix U. In the following, we will talk about how to decompose this matrix A into the L and U. But here, just think about we already have the matrix L and matrix U. Then, using this factorization, using A is going to be L times U. Then, to solve the A equals B, when P is equal to like that. Okay. Okay. So first of all, to solve this equation, this matrix equation using the LU decomposition, there is a two sub problem, right? Ly times b and ux times y, right? So first of all, let's think about the Ly times b. So to find the matrix, to find the solution y here, we can row reduce this augmented matrix L times B. I know not M times B, L and B as a I times Y. Okay, so in other words, okay, this matrix L has a identity matrix as a reduced echelon form of the matrix L. Okay, so if you go back to the last week lecture, we can say that this matrix L has the identity matrix. This is identity matrix, right? Identity matrix as a reduced echelon form. Okay. Okay. So first of all, how can we row reduce from here to here? How can we do that? How can we do that? We have to eliminate this one and this one and this one, and then have to remove this one and this one and this one, right? Then how can we do that? First of all, this term, let's say, this term. Let's just think about this one. Okay, let's let's do first this. Okay. Okay, so first of all, to eliminate this term and this term and this term, we can compute the R2 plus 1 times R1, right? So in this case, just 1, 1, 1, In this case, negative 2, right? So just remove this one, but this is still negative 5, right? So like that. 1 is here, still here. Then plus 3, so it will be like 3, 1, right? So negative 9 here. Then what is that? 5 plus negative 9, right? This one term 7. Okay, let's write like this. 1 times negative 9 minus 2 times negative 9. Okay, then 11 times what? Plus 3 times negative 9, like that, right? Okay, so specifically, to make this term as zeros, there is the 3 multiplication with the 3 addition, right? Then we have to remove this term and this term, right? So by using this row reduction algorithm, we can derive this one to the finally this one. Okay, so but in this every procedure, okay, there is the, in this case, a 3 multiplication, 3 addition, right? What about this? There will be the 2 multiplication and 2 addition, right? Because to eliminate this one and this one, we only compute the new values here and here, right? Then what about this one? We only have the 1 multiplication and 1 addition, right? So finally, to low reduce this original matrix LP as a IY, there are 1, 2, 3, 4, 6 multiplication and 6 addition. 6 multiplication and 6 addition, right? Okay, so anyway, we get the vector u here, right? Then what next? With y-axis equal to x is equal to y, then we have to find the matrix X. Then how? We can do same way, same things. From uy, we can derive the X and identity matrix by using the row reduction algorithm. Then how? First of all, we have to make this matrix U as a identity matrix. So first of all, we have to make this term as a 1, 1, 1, right? By using some kinds of the matrix scaling law operation, right? And then remove this one, right? Using this term, something like this, right? We already know how to do that, right? So but in this case, let's just think about the number of the operation, number of flop. Okay, so for example, when creating the column 4 here, when creating the zeros in column 4 here, it requires the 4 division in row 4. What does it mean? What does it mean? Why we need 4 division? 4 row division? Why? First of all, okay, so this is row 4, right? So first of all, to eliminate this term by using this one, then we have to normalize this one as 0, as a 1, and just add this one and this one, right? What about this one and this one? We have to normalize this term as a 1 and multiply by -2 to eliminate this one, right? Finally, to eliminate this one, first of all, we have to normalize this one as a 1, and then we have to multiply -2 to eliminate this one, right? Then, to summarize, when eliminating this one, and this one, this term will something like what is that, right? 1 times 1, right? We have to do here and here, right? So 5, then plus 1 times 1, right? So in this case, -4 plus 2 times 1, something like that. And -9 plus 2 times what? 1, something like that. So here there is the 4 division, 3 multiplication, and 3 addition, right? Similar to the here, right? So anyway, if you do similar things on the remaining part here, then we finally get the new matrix, a new vector x here. So it will be the final answer of our matrix, matrix equation. So it means that the solution of the ax equals b with a looks like that, b looks like that, the solution x will be like that. But in this case, there is the 4 division, 6 multiplication, and 6 addition during row reduction algorithm. So to summarize, to find the vector x, it requires a 28 arithmetic operation or the floating point operation, okay? Because there is the 4, 6, 6, so it means 16, and there is the 6, 6, and 12, so it will be the 12 and 12 and what's that? 16, right? So it will be the 28 arithmetic operation if we using the LU decomposition, right? In contrast, if you just try to solve the ax equals b directly by row reduce a b to the ix, it takes about 62 arithmetic operation. So we can say that by using the using LU decomposition is much easier to solve and more efficient than the original matrix solver. X is going to be inverse B, something like that. Okay, so this is the advantage of the LU decomposition or the LU factorization. Okay, from the next lecture, we will talk about how to derive the LU decomposition from the original matrix A. Okay, thank you.